Hi there! Welcome to the 9th episode of the design and construction of a curve tracer. In this episode we will see how I measure the ramp and ladder voltages and the currents and display these measurements on an LCD. And if you are thinking I used the Arduino to do so, you guessed right. In fact, using the Arduino for this part of the project was the primary reason I chose to generate the signals with it in the first place. Since I had to use it anyway for taking these measurements, there was no reason to add extra logic circuit to generate the ramp and the ladder, as some of you proposed in your comments. I would also like to apologize for the long wait before releasing this new video on the curve tracer. Unfortunately, I had to spend more time than anticipated fine-tuning the final details of the device to make it work exactly how I intended. I will explain all the crucial points during the video itself. But now, let's get into the details with no further ado. Using an Arduino to generate the ramp and ladder signals allows us to know exactly when the ramp reaches its peak value and when the ladder is within its first step. In fact, we can simply introduce a few checks in the code that generates these signals to determine their current state. From there, it is very easy to sample each of the two signals at the precise moment, directly from the points where they are provided to the device under test or DUT, and feed them into one of the analog-to-digital converters available on the Arduino Nano. Additionally, we can choose the exact moment in the code to take the readings and output the information to the LCD connected to the Arduino, and we can also control the frequencies of these readings to minimize any potential interference with the generation of the two signals. So, as you can deduce from this, using an Arduino as the core of this project offers significant benefits for easily obtaining a complete set of information for the DUT. Let's now take a look at the changes in the schematic necessary to add this functionality to the curve tracer. I have integrated the new measurement circuitry directly into the same schematic used for generating the ladder and ramp signals, and this allows me to show you precisely how the new components connect to the Arduino. First, on the upper left side, you can see the block representing the LCD display. I have chosen an LCD that communicates with the Arduino via the I2C protocol. This simplifies the wiring, requiring also two wires from the Arduino to control the LCD. In particular, the Arduino Nano uses pin A4 and A5 for I2C communications. As you can see on the Arduino Nano pinout, A4 is for the SDA signal, the serial data, and A5 is for the SCL signal, the serial clock. These two pins are therefore connected to the corresponding SDA and SCL pins on the LCD module, and the LCD module is then powered by connecting the plus 5V power supply with two additional wires. Here is the datasheet for the LCD I decided to use. Notice that the display has 4 lines with 20 characters per line, which is plenty of space to show all the necessary information simultaneously. While the LCD controller itself often uses a 4 or 8-bit parallel data bus, similar to the well-known 2002 LCD, the module I am using has a small daughter board on the back. This board contains a communication chip that handles the I2C protocol, converting the serial data from the Arduino into the parallel signals required by the LCD controller. To make things even better, this daughter board includes a small trim pot to control the display contrast, and this eliminates the need for any external circuitry for contrast adjustment. To minimize the computational load on the Arduino for converting the analog-to-digital converter readings into meaningful values on the LCD, I have decided to perform most of these conversions directly in hardware using a couple of op-amps within a single LM358 integrated circuit. Here on the upper op-amp, you can see that it adjusts the level of the ramp signal taken directly from the ramp amplifier. Resistors R29 and R30 form a voltage divider that scales down the ramp voltage to an appropriate level ensuring that a maximum ramp peak value of plus 11 volt can be read within the Arduino ADC range. The op-amp acts as a buffer, providing a high input impedance to prevent loading of the voltage divider and ensuring an accurate voltage reading. Similarly, resistors R31 and R32 handle the ladder signal using the other op-amp within the same LM358 package. The ladder signal is taken from the voltage ladder of the level adjustment circuit, which is the same voltage applied to the control pin of the devices under test. The challenge here is that the voltage we need to measure can be both positive and negative, but the Arduino ADCs can only handle positive voltages between 0 and plus 5 volts. To address this, we need to rectify these signals so that only positive voltages are fed to the analog-to-digital converters. The most straightforward approach to rectification is using a full bridge rectifier. However, the forward voltage drop across the diodes in a standard bridge rectifier would significantly affect the readings, especially for small signal values below approximately 0.7 volt, and that makes accurate measurements of these lower voltages practically impossible. In short, we need a full bridge rectifier with virtually no voltage drop, a problem that took some time to solve. After researching various solutions, I came across a design from Texas Instruments that creates a precision full bridge rectifier suitable for voltage measurements and using only a couple of diodes and op-amps. Here is their technical article. The circuit is designed such that the two diodes effectively create a full wave rectifier from the positive and the inverted negative half waves of the input signal. The connections are configured to pre-bias the diodes close to their forward voltage threshold, and this ensures that even a minimal input voltage will cause them to conduct immediately, which is exactly what we need to accurate low voltage measurements. I will provide a link to this paper in the archive available on my website, eleneasy.com, for those interested in understanding the detailed operations of this circuit. Back to the schematic, I have implemented two of these precision rectifier circuits to convert both the ramp and the ladder signals into positive-only voltages suitable for measurement by the Arduino NANO's ADCs. Here is the first precision rectifier used for the ladder signal, and here is the second used for the ramp signal. The outputs of these rectifiers are connected directly to specific analog input pins on the Arduino. I have used A2 for the ladder measurements and A3 for the ramp measurements. And that is all for the new hardware additions. Let's now move on examining the new Arduino code required to make all of this work as intended. Here is the latest version of the software for the curve tracer. Let's examine the new additions. First, to manage the LCD with I2C communication, I have included a new library, liquidcrystal_I2C.h. Following this, there is a section containing several variables and constants related to the measurements. The first three variables, ramp voltage, step voltage, and step current, will hold the current measurement values displayed on the LCD. The next three variables store the corresponding previous readings. This will be used to determine whether updating the information on the display is necessary. Read ramp voltage and read step voltage are Boolean flags used to control whether a new measurement should be taken for the ramp and for the step signals respectively. The variables read ramp and read step will store the raw analog to digital converter readings for the ramp and the step signals before any conversion. And finally, the constants max ramp count and max step count define the number of loop iterations to skip between consecutive readings of the ramp and the step signals. This is basically a throttling mechanism. Well, you see, since the Arduino is also responsible for generating the ramp and ladder signals, we must avoid overloading it with other tasks. Otherwise, the quality and frequency of the generated signals could be negatively impacted. Therefore, we perform readings with a much longer period than the signal generation frequency, and we refresh the display only when a significant change in the measured values occurs. Additionally, we stagger the readings of the ramp peak voltage and the ladder step voltages to prevent two consecutive readings or display updates from happening too close to each other. The max ramp count and the max step count constants serve exactly this purpose. Specifically, we take one reading of the ramp peak approximately every 500 iterations of the loop function, and we take one reading of the ladder step approximately every 4 ramp readings. Moving on, we have 3 more constants defining the LCD parameters. 0x27 is the hexadecimal I2C address of the LCD module. 20 represents the number of columns, and 4 represents the number of rows. In the setup function, we first initialize all the newly defined variables. Then we initialize the LCD screen using the new CT-LCD object. Turn on the backlight for better visibility, position the cursor to the top left corner, and print a welcome message that also includes the current software version running on the Arduino. Next, we pause for a couple of seconds to allow the user to read this initial information. After the delay, we print some default labels for the voltage and current values on the display. The way these strings are formatted will simplify subsequent screen updates, as we will only need to replace the numerical values rather than rewriting the entire display content. The reading of the sensor data and the display of the information are both handled within the loop function. However, to improve code organization, these actions are performed by 2 separate functions, one for taking measurements and one for printing the information. These functions are then called within the main loop. This function here, which I've named step measurements, is responsible for taking the actual measurements. These measurements are executed only when their corresponding flag is true, otherwise the measurement is skipped. We'll see where these flags are set in the main loop later. For now, it is important to understand that when a flag is set, we read the output of the corresponding analog-to-digital converter using the Arduino's built-in analog read function. Once the reading is complete, we immediately set the corresponding flag back to false, preventing further readings until the main loop sets it to true again. After a reading is taken, the step print function is called to update the display. This measurement procedure is essentially the same for both the ramp peak voltage and the ladder step voltage. Now let's examine the step print function. Don't pay too much attention to its name and the one of the previous function. It doesn't exclusively refer to measurements of the ladder steps. The term step here was intended to mean a step in the printing process, not the name of the signal being measured. Yeah, I know, I should have chosen a better name for it, but at this point I'm not going to change it anymore. Here is how the step print function works. Each time this function is called, it compares the current reading of a measured value with its previous reading. The display is updated only if these two values are different. The first check is performed on the ramp voltage. If the new ramp voltage is different from the previous ramp voltage, we update the voltage value displayed on the screen, including repositioning the decimal point if necessary. To do this, we take the integer ramp voltage, which represents the raw ADC reading, and divide it by 100. Since these values represent a scaled voltage 0 to 5 mapped to 0 to 1023, this division isolates the integer part of the voltage. We then print this integer part. Next, we print the decimal point, followed by the fractional part of the voltage, which we obtain by taking the modulo 100 of the original integer ramp voltage. This process is then repeated for updating the step voltage on the display, but only if current step voltage differs from previous step voltage. And finally, we calculated the step current based on the step voltage and display it as well. This calculation is possible because the step current is directly proportional to the step voltage, due to the characteristics of the Howland current pump circuit used for voltage to current conversion. We will continuously display both the step voltage and the step current, regardless of the active test mode. It's important to remember this during component testing. Only the measurements relevant to the specific test being performed should be considered valid. The other displayed value might not be meaningful and could lead to incorrect interpretations. Let's now look at where the read ramp voltage and read step voltage flags are set to true in the main loop, and where the step measurements function is called. The read step voltage flag is set to true on line 220. This line is reached only when the condition in the if statement on line 212 is met. This condition becomes true when the ramp reaches its peak and the ladder completes its first step. Additionally, we need to enter this section of the code 125 times, based on the max step count value, before we actually set the flag. When we finally set the read step voltage flag to true to initiate a reading, we also reset the counter associated with it, so we will need to enter this section again another 125 times before the next step voltage reading is taken again. On lines 227 to 237, a similar process occurs, but this time to set the read ramp voltage flag to true for reading the ramp peak voltage, rather than the first step of the ladder. The delay here is controlled by max ramp count. Once both these conditional checks and the potential flag settings are completed, we call the step measurements function, which will then execute only those readings for which the corresponding flag has been set to true. All the remaining code is the same as described in a previous episode and is dedicated to the generation of the ramp and ladder signals. Let me now briefly demonstrate how this software, along with the new hardware additions, works in practice. And there you have it. This is the completed and working prototype of the curve tracer. It is now time to assemble all the circuitry in a nice case, full of controls and a nice LCD. But this will be the subject for our next video on the curve tracer. And while waiting for it, I offer to you my usual happy experiments.